Mining the moon begins, the race to extract rare helium-3 for Earth's future. A new dawn in space exploration. The moon, our silent companion in the night sky, has always captivated the human spirit. For centuries, it has inspired stories, guided explorers, and stood as a symbol of what lies beyond. But now, it may offer something far greater than dreams, a real solution to Earth's energy crisis. Welcome to KM's Celestial Journey. In today's episode, we unravel a breathtaking mission that could reshape the very foundation of modern life as we know it. A small startup from Seattle, Interlune, has launched a bold initiative. Their target? A rare and almost magical element hidden deep within the moon's surface, helium-3. This isn't just a mining operation. It's not just another space tech venture. This is the beginning of a new chapter in human history. And we're here to tell you that story. The silent miracle hidden in lunar dust. Long before rockets ever reached the moon, before satellites orbited Earth, and before humans looked up and dreamed of walking on another world, something extraordinary was already happening, quietly, invisibly. The sun, our magnificent, fiery star, was flooding space with energy. Not just light, not just heat, but something far more rare, far more powerful. Helium-3. This tiny, lightweight isotope was being carried by the solar wind for billions of years. Earth, protected by its magnetic field and thick atmosphere, deflected most of it away. Almost none of it reached our surface. But the moon? The moon, with no atmosphere, no magnetic shield, simply absorbed it for billions of years, quietly, steadily, layer by layer. And now, in the 21st century, humanity is finally beginning to understand just how valuable that quiet accumulation may be. A sleeping giant in the dust. Helium-3. It's not radioactive. It's not toxic. It doesn't create nuclear waste. And yet, when used in nuclear fusion, it holds the potential to generate massive amounts of clean, safe energy. That's right, clean energy from nuclear fusion. Unlike the dangerous and complex fission reactions we use today in nuclear power plants where atoms are split apart, fusion joins atoms together. It's the same process that powers our sun. But here's the twist. Almost all fusion reactions on Earth today use deuterium and tritium, both hydrogen isotopes. Tritium, in particular, is radioactive and incredibly difficult to handle. Now imagine a better option. Helium-3. When fused with deuterium, helium-3 releases immense energy, but almost no radiation, no dangerous neutrons, and no need for elaborate shielding. It's a dream fuel, a miracle waiting to be harvested. And it's just sitting there, embedded in the moon's surface. This isn't a science experiment or fantasy theory. This is real science. Real physics, backed by decades of research carried out by NASA, the Department of Energy, and laboratories across the world. We've known about helium-3 for years. What we didn't have until now was a serious plan to go and get it. Earth's helium-3 problem. Here on Earth, helium-3 is painfully scarce. It's produced in only trace amounts, often as a byproduct of nuclear weapons programs or decaying tritium in warheads. That means the global supply is not just tiny, it's also unreliable and tied to outdated Cold War infrastructure. Right now, the entire world produces just a few kilograms of helium-3 per year. And yet demand is growing. Fast. Why? Because helium-3 isn't just a possible fuel for the power plants of tomorrow. It's already crucial for the technologies of today. Helium-3 is used in neutron detection, medical imaging, cryogenics, and most notably, quantum computing. Quantum computers, those strange, futuristic machines that are poised to solve problems classical computers never could, must operate in environments colder than outer space. And helium-3? It's one of the few substances that can cool systems down to those unimaginably low temperatures. In a world racing toward quantum breakthroughs, helium-3 is the enabler. In a world desperate for clean energy, helium-3 is the answer. And in a solar system full of rocky planets and empty space, the moon is the only nearby place where we can find enough of it to matter. The physics behind the promise. Let's take a deeper look at what makes helium-3 so special. A fusion reaction between helium-3 and deuterium can produce a proton and a large amount of energy without releasing any dangerous neutrons. That means no radioactive waste. And because the reaction is anatronic, the reactor components won't become radioactive themselves, drastically reducing long-term maintenance, shielding, and environmental risk. For power companies and governments, that's an enormous advantage. Now consider this. 1 ton of helium-3, roughly a truckload, could theoretically power a city of 1 million people for an entire year. Yes, you heard that right. 1 ton, 1 million people, 1 year. And on the moon, experts estimate there could be up to 1 million tons of helium-3 embedded in the top few meters of lunar soil. Let that sink in. We're not talking about thousands of barrels of oil. We're talking about a nearly inexhaustible supply of clean, powerful, revolutionary energy, waiting just 240,000 miles away. Why haven't we done it yet? So with all this promise, why hasn't humanity been mining the moon for helium-3 already? Well, because getting there is hard, and mining there is even harder. You see, helium-3 isn't just sitting in little pockets we can scoop up. It's spread out across the lunar regolith, the dusty, rocky surface layer of the moon. To extract it, we'd need to heat that soil to over 600 degrees Celsius, in harsh, freezing temperatures, with no air, no water, and intense radiation from the sun. That's a lot of energy, a lot of logistics, a lot of risk. Plus, there's the question of how to transport helium-3 back to Earth. It's a gas, after all. Not the easiest thing to launch in a rocket, and with every extra ounce of weight, launch costs skyrocket. And yet these challenges aren't impossible. For the first time in history, we have the tools, we have the materials, the robotics, the computing power, the spacecraft. And now, thanks to Interlune and a new wave of space entrepreneurs, we also have the vision. The vision to stop dreaming and start doing. What's at stake? Let's be blunt. We are running out of easy energy. Fossil fuels are choking our atmosphere. Nuclear fission comes with deadly risks. Solar and wind, while promising, struggle with intermittency and scalability. Helium-3 offers something different. A way to generate power without poisoning the planet. A way to run machines without burning anything at all. A way to leap beyond the limitations of Earth-based energy forever. But it's not just about electricity. Think about what energy means for the developing world, for the climate crisis, for space exploration itself. With helium-3 reactors, we could one day power entire lunar bases, send crewed missions to Mars, or transform deserts into farmland. This is more than fuel. This is potential. Pure, untapped, unprecedented potential. Interlune's mission, one giant leap for private space industry. The year is 2025, and while Earth grapples with rising energy demands, unstable fossil fuel markets, and an ever-pressing need for sustainability, a new frontier quietly awakens above us. Far beyond the clouds, beyond satellites and space stations, lies a dusty, silent world, the moon. A place that for decades has been treated as a trophy from the space race. But now it's being seen as the next major resource hub for humanity. At the center of this unfolding cosmic revolution is not NASA, not SpaceX, but a lesser-known, sharply focused startup from Seattle, Interlune. This small but ambitious company has taken a leap that most would fear to even dream. Their goal isn't tourism. It isn't Martian colonization. It's something far more immediate, far more grounded in today's global needs. Helium-3. But how exactly do you even begin to do that? How do you reach across 384,000 kilometers of empty space and extract something buried in lunar soil, then send it back to Earth safely and profitably. Interlune has a plan, and not just a vision on paper, but a carefully laid out three-phase roadmap that is already in motion. Let's break it down. Phase 1, Crescent Moon. The journey begins, not with shovels or drills, but with data. Phase 1, aptly named Crescent Moon, focuses entirely on scouting the lunar surface from orbit. Now, this isn't just about pointing a telescope and hoping for the best. Interlune is deploying a state-of-the-art hyperspectral imaging system, a specialized camera capable of reading the moon's surface in more detail than any human eye, or even most satellites, ever could. This camera doesn't just take pictures. It analyzes light frequencies reflected off the moon's regolith, its surface dust and rock. And in those reflections, it can detect the chemical signatures of helium-3. We're talking about mapping the invisible. These spectral images will allow Interlune scientists to pinpoint specific regions where solar winds have deposited high concentrations of helium-3 over billions of years. But there's more to this than just finding the hotspots. Crescent Moon is also about understanding the terrain, its elevation, temperature fluctuations, radiation exposure, dust movement, and structural integrity. Because before anyone can land, dig, and extract, they need to know exactly what they're working with. This is not guesswork. It's precision space analytics, and it's already underway. The data gathered from Crescent Moon will determine where Phase 2 will unfold. And that's when things get even more intense. Phase 2, Prospect Moon. Now that the team knows where the helium-3 is, it's time to get boots on the ground, or rather, wheels and claws. Enter Phase 2, Prospect Moon. This is where Interlune plans to land an autonomous robotic prospector on the lunar surface. Think of this machine as a combination of geologist, chemist, and miner, all rolled into one artificially intelligent payload. It's equipped with tools designed to drill, dig, analyze, and sample lunar soil in real time. But the goal here isn't to extract helium-3 yet, not fully. It's to test the process. Can the machinery survive the moon's brutal conditions? Can the fine, clingy lunar dust, which has been known to destroy equipment, be managed? Can helium-3 be separated from the regolith efficiently on-site? These are not rhetorical questions. These are critical roadblocks that must be solved. The robotic lander will attempt to simulate the real mining process, using scaled-down versions of what Interlune hopes to deploy later. It will run tests on site, performing small-scale extractions and analyzing soil samples to determine the most effective refinement techniques. And all of this is happening over 200,000 miles away from the nearest human mechanic. The robotics must be self-sustaining. The AI must be smart enough to adapt. And the mission control back on Earth must be capable of guiding and recalibrating operations in near real time, despite a 1.3-second communication delay. Prospect Moon isn't just a test run, it's the backbone of everything that comes next. What works here will define how helium-3 is harvested, how it's processed, and how it's ultimately transported off the moon's surface. Because once Prospect Moon provides the answers, Interlune plans to go all in. Phase 3, Harvest Moon. This is the phase that will change everything. Harvest Moon is where dreams, tests, and simulations end, and the real mining begins. The plan is bold, almost unimaginable by 20th century standards. Interlune intends to build and deploy a fleet of robotic harvesters, automated miners designed to operate under extreme conditions. These machines will begin to systematically extract lunar regolith, the dusty, jagged topsoil of the moon, and isolate the valuable helium-3 trapped inside it. But here's the tricky part. You don't just dig up helium-3. It's not sitting in chunks, waiting to be scooped up. It's dispersed very sparsely within the lunar soil. So the harvesters will need to process hundreds of tons of regolith to extract just a few pounds of usable helium-3. That requires incredibly efficient refinement systems that can work with minimal power, operate autonomously, and filter out this rare isotope without wasting precious resources. The extracted helium-3 will then be compressed, stored in specialized cryogenic containment units, and loaded onto lunar payload rockets. Yes, payloads from the moon back to Earth. This isn't science fiction. This is what Interlune is actively preparing for. The company plans to use reusable space vehicles, potentially leveraging orbital transfer stations to rendezvous with Earth return shuttles. The entire logistics chain, from lunar launch to Earth re-entry, must be meticulously calculated. Every gram counts. Every movement must be perfect. And there's no room for second chances. The cost of a failed payload, or worse, a catastrophic re-entry, could set the project back years and drain millions. But if it works, if just one payload makes it safely back, filled with purified helium-3, it will mark the first time in human history that a resource has been mined from another celestial body and used for energy production on Earth. Let that sink in. Not gold, not oil, not water, but helium-3, a clean-burning, non-radioactive isotope capable of transforming global energy infrastructure, harvested from the moon and brought back for Earth's future. And Interlune intends to do it not once, but over and over again. They're designing the entire operation to be scalable. More mining units, more payload launches, more lunar outposts. Eventually, they envision a self-sustaining helium-3 mining colony, fully robotic, powered by solar energy, operating around the clock in the moon's relentless environment. From resource-starved Earth to the energy-rich plains of the moon, Interlune is leading the way in what could become a multi-trillion-dollar lunar economy. But none of this happens without each phase succeeding. And with every phase comes unimaginable engineering challenges, political roadblocks, and ethical dilemmas. But one thing is clear, the mission is already in motion, a $20 million substance that could power our world. You might be wondering, just how valuable is helium-3? Let's put it this way. Just 2.2 pounds of helium-3 is estimated to cost around $20 million. That's not a typo. $20 million. And here's the kicker. It's not just about the price tag. The economic impact of using helium-3 in clean energy and quantum computing could skyrocket global innovation. We're talking about powering cities with nuclear fusion reactors that leave behind no toxic waste. We're talking about computers that solve problems in seconds that would take today's supercomputers years. Helium-3 has the power to drive a technological renaissance. But the race is on, and Interlune isn't the only player. Space politics and the new lunar gold rush. In the quiet vacuum of space, there is no sound, no winds whisper, no thunder roars. But if you listen closely, not with your ears, but with your understanding, something monumental is happening. A silent race. Not of men running tracks, but of nations, corporations, and visionaries racing for something far more valuable than metals. They are racing to own the moon. Not the craters, not the shadows, not the flag planted in 1969. No, they are after what's buried in its soil, a whisper of gas, a ghost of an element, helium-3. And this new gold rush isn't being led by space agencies alone. It's not just NASA or the European Space Agency. It's companies, private companies, tech startups with grand ambitions, and investors who dream not just in dollars, but in decades. Interlune, that modest Seattle-based startup we've been following, is no longer just a technical venture. It's now part of something bigger, something global. A high-stakes geopolitical game with the moon as the chessboard. But here's the twist. The rules of this game were written over 50 years ago, and they're falling apart. Let's rewind. In 1967, as the world teetered between space dreams and Cold War fears, global powers came together to draft a set of principles, the Outer Space Treaty. This document, signed by over 100 nations, was a kind of promise, a pact. That outer space, including the moon, would belong to no one. No nation, it declared, can claim sovereignty over the moon. No military bases, no nuclear weapons, no conquest. It was idealistic, beautiful even. A vision of space, not as a battlefield, but as a sanctuary, a neutral zone for all humankind. But now, more than half a century later, that vision is cracking. Because no one anticipated this moment. A time when mining the moon is not science fiction, but corporate strategy. And the treaty? It never accounted for private enterprise. It said nothing about companies like Interlune launching robotic landers to extract lunar resources. So now the world is watching, caught in a legal gray zone. Can you own what you mine, even if you don't own the land? Can helium-3 pulled from the moon be sold, taxed, patented? And if so, who decides? These questions aren't just hypothetical. They're urgent. Let's paint the picture. Imagine Interlune successfully completes its mission. Its robots dig into the regolith. They extract helium-3. They load it into a return capsule and launch it home. The capsule lands on Earth. Boom. Lunar helium-3 in the hands of a private company, ready to fuel reactors or power quantum computing systems. A triumph? Yes. But also a spark. A spark that could ignite a firestorm of legal, economic, and political disputes. Because once Interlune proves it can be done, everyone will want in. China, Russia, India, the EU. Tech giants, defense contractors, energy conglomerates. And with that, the real race begins. Not for exploration, but for extraction. Let's take a closer look at the players. China has already declared its ambitions to mine the moon. Their Chang'e missions have brought back lunar samples. They've mapped helium-3 deposits in key regions like the Mare Tranquillitatis. Beijing isn't just studying the moon, it's strategizing. Reports suggest they've begun drafting their own legal frameworks, China-centric lunar mining laws for future implementation. And what about Russia? Their Roscosmos agency is aging, but their ambitions remain sharp. Russia has spoken openly about creating permanent lunar stations. There's even talk, whispers in diplomatic corridors, of a future lunar alliance between Moscow and Beijing. A shared base, a shared refinery, a shared stake in the helium-3 boom. India is quietly ramping up too. Chandrayaan-3 was just a taste. The Indian Space Research Organization, ISRO, is aligning with national tech firms to discuss lunar payload capacities for future mining missions. Europe, traditionally more cautious, is now catching up. ESA has floated concepts for lunar ISRU, in situ resource utilization, using rovers to melt, sift, and separate lunar dust for valuable elements. Even Luxembourg, a tiny country, has become a heavyweight in space finance. They've passed laws supporting space resource rights and investments. And don't forget the United Arab Emirates, Japan, and South Korea, each with growing space programs and lunar ambitions of their own. It's not just a few nations anymore. It's the entire global stage. Now let's bring it back to Interlune. What happens when a US company becomes the first to bring helium-3 back from the moon? Do they get to keep it? Sell it? Patent a method of extraction and license it to the highest bidder? And here's the bigger issue. What if others don't agree? What if China claims Interlune's mining site violates the spirit of international law? What if Russia argues that no private entity should control such a vital energy resource? Or what if another company, say from Europe, says, "Hey, we mapped that region first. You're trespassing." Without updated space law, it's the Wild West. On the moon. Let's dive deeper. In 2015, the US passed the Commercial Space Launch Competitiveness Act, giving American companies the right to own and sell resources mined from space. To many, this was groundbreaking. It gave firms like Interlune legal backing to pursue lunar mining. But to others, especially rival nations, it was provocative. China criticized the move as unilateral and in contradiction to international norms. Russia called it a direct violation of the spirit of the Outer Space Treaty. So now we have a situation where the US says companies can own what they mine. But the rest of the world isn't so sure. And the Outer Space Treaty? It's still the official document, but with loopholes big enough to drive a lunar lander through. It forbids sovereign claims. But it doesn't address resource ownership. It promotes peaceful exploration. But it doesn't regulate private competition. It was written in the age of Sputnik and Apollo, not in the age of Elon Musk, Jeff Bezos, and Interlune. But it gets even more complicated. What if mining damages the lunar environment? Unlike Earth, the moon has no oceans, forests, or weather systems. But it does have a unique ecosystem, one we barely understand. The dust is sharp and electrostatically charged, crucial for lunar chemistry. What happens when we dig it up, heat it, strip it of helium-3, and dump the residue? Do we risk harming future scientific research? Or worse, rendering key regions of the moon permanently unusable? Who monitors this? What agency oversees environmental impact assessments on the moon? As of now, no one. Then there's the question of militarization. The 1967 treaty forbids weapons of mass destruction in space. But it says nothing about satellite surveillance, anti-satellite missiles, or armed defensive mining equipment. If helium-3 is as valuable as it seems, worth more per gram than gold, platinum, or uranium, how long before someone decides it needs to be protected? Could nations build security outposts near key mining zones? Could we see lunar orbit patrolled by satellites carrying kinetic weapons? It may sound extreme, but history shows us wherever there are valuable resources, there is conflict. And on the moon, there are no borders. No national flags that grant territorial rights. Just gray soil, silent craters, and a growing sense of ownership where none exists. Meanwhile, legal scholars, diplomats, and technologists are gathering in think tanks, virtual summits, and closed-door sessions, trying to redefine what space law should be. They speak of mutual benefit, multilateral agreements, shared governance. But none of it is binding. And the missions, they're already launching. By the time a new treaty is signed, it might be too late. Claims will have been staked, resources extracted, fortunes made. And the moon? It will never be the same. Let's return once more to Interlune's quiet offices in Seattle. Their plans are bold, their vision ambitious. But they've also stepped into a geopolitical minefield. They are not just engineers now. They are pioneers at the center of a collision between law, ambition, and the unknown. The moon, once thought to be silent and still, is becoming the most contested ground in the history of humankind. And the helium-3 hidden beneath its dust? That's not just a scientific curiosity anymore. It's the new oil, the new gold, the new power. And everyone wants a piece. The challenge is ahead, a story of cosmic obstacles and earthly determination. The dream is monumental. The vision is clear. Mining helium-3 from the moon and returning it to Earth promises to be a revolutionary step forward in human civilization, one that could rewrite how we think about energy, computing, and our place in the universe. But as bold and visionary as this mission is, the road to success is littered with challenges, enormous ones, and each challenge tells its own story. This is not just a technical endeavor, it's a full-scale interstellar symphony of science, risk, perseverance, and uncertainty. Let's dive deep into the real hurdles Interlune must face on its mission to mine the moon. The silent, hostile world of the moon. Imagine landing on a place where the sun can scorch you with 127 degrees Celsius of heat. And then, in a matter of hours, you're plunged into a deadly freeze of minus 173 degrees Celsius. That's the moon for you. It's not just cold and hot, it's unforgiving, unpredictable, and completely alien. There's no atmosphere to shield you, no wind to carry a breeze, no water to quench a fire. And most of all, no margin for error. Lunar dust, for instance, may sound harmless, but this isn't the dust you sweep under your couch. Lunar regolith is razor-sharp, highly adhesive, and electrically charged by solar radiation. It clings to machinery, grinds away at joints and gears, and damaged more than a few Apollo-era instruments. Interlune's robotic landers, rovers, and drills will need to function in this dusty, abrasive environment for extended periods, without the help of on-site technicians. Every moving part has to survive the moon's deadly days and nights, temperature swings, micrometeorite impacts, and intense solar radiation. It's like sending a surgeon into a sandstorm with no backup and expecting them to operate flawlessly for months. That's the level of pressure these machines will face. Digging for atoms, the challenge of helium-3 extraction, but surviving the moon is only the beginning. The real challenge? Finding, extracting, and refining helium-3. Helium-3 isn't just sitting there waiting in shimmering pools under the surface. It's deeply embedded in the lunar soil, scattered in concentrations so low that thousands of tons of regolith must be processed to collect a small quantity. To get just a gram of helium-3, you may need to dig up over 150 tons of lunar dirt. That's not a metaphor. That's the math. So how do you mine a molecule? Interlune will need robotic systems that can excavate large swaths of regolith, heat it to extreme temperatures, more than 600 degrees Celsius, and then capture the helium gas released during the heating process. These robots must operate autonomously. There's no joystick in Houston to steer them. The delay in communication between the Earth and Moon makes real-time control impossible. That means AI-driven mining bots must make their own decisions in an environment humanity has only tiptoed across. Every gram of helium-3 recovered will be a testament to engineering brilliance and sheer grit. Lifting off from the moon, the transportation nightmare. Even if the robots mine helium-3 successfully, Interlune still has to tackle one of the most underappreciated challenges in space exploration, getting off the moon. That's right. It's not enough to land and dig. You have to launch the harvested material back into lunar orbit and then transport it over 384,000 kilometers to Earth. Lifting off from the moon might sound easier than from Earth due to the lower gravity, but it's far from simple. There's no launch pad, no repair crews, no safety nets. Imagine launching a fragile cargo at millions of dollars in value from an unstable, uneven surface, relying entirely on machines. Everything must work perfectly. The rocket engine must ignite in freezing darkness or scorching daylight. Guidance systems must function without fault. And above all, the payload must survive the violent forces of launch and space travel. Once it escapes the moon's grip, it enters a delicate ballet of orbital mechanics, aiming for Earth, timing the re-entry window with surgical precision. And what's inside that spacecraft? Just a few grams of gas, worth more than gold, more than diamonds, more than almost anything on Earth. Lose it, and you've wasted a multi-million-dollar mission. Refining helium-3, a puzzle still unsolved. Back on Earth, another invisible enemy awaits, the refining process. Helium-3 has never been mined at this scale before, not even close. The infrastructure simply doesn't exist. Interlune isn't just inventing the method to collect helium-3, they're also being forced to pioneer the techniques to refine and store it. How do you handle a gas that only exists in trace amounts? How do you isolate it from the more common helium-4? How do you ensure it stays stable, cool, and safe in transit? These questions don't have easy answers. In fact, the entire supply chain, from moon to Earth to energy grid, needs to be built from scratch. Every valve, every tube, every cooling system must be custom-made to handle something we've barely touched before. There's a real risk that we get helium-3 to Earth only to discover we're not ready to use it. The giant of red tape, legal, political, and ethical minefields. Then there's the issue of legality. Who owns helium-3? According to the Outer Space Treaty of 1967, celestial bodies are not subject to national appropriation. But it says little about private companies extracting resources. Some argue that mining the moon violates the spirit of the treaty. Others say it's perfectly legal. But the truth is murky. Interlune is treading legal ground that no company has walked before. What happens if another nation claims the same lunar region? What if China or Russia sets up its own helium-3 base nearby? What happens if a mission fails and debris spreads across another country's designated zone? These aren't hypotheticals. These are scenarios very likely to unfold within the next 2 decades. And beneath those legal debates lies an even deeper ethical dilemma. Should we mine the moon at all? Do we risk turning our nearest celestial neighbor into just another resource pit? Do we treat it as a frontier or as a sanctuary? Interlune may have a business plan, but Earth doesn't yet have a cosmic moral compass. Money, the eternal barrier. Finally, there's the problem of funding. Missions like this don't come cheap. Every rover, every lander, every gram of helium-3 transported back to Earth represents tens of millions of dollars in research, construction, testing, and logistics. Even with venture capital and government support, there's no guarantee the cash will keep flowing. Investors are notoriously fickle when returns don't come fast. And helium-3 is a long play, a very long play. What if early missions fail? What if helium-3 doesn't deliver on the promise? What if a rival company swoops in and beats Interlune to the prize? These aren't just technical questions. They're existential ones. Because at the end of the day, no vision, no matter how revolutionary, survives without fuel. And in our world, that fuel is money. To succeed, Interlune must become more than a startup. It must become a symbol of confidence, a name that investors, scientists, engineers, and global leaders can rally behind. And that kind of trust, it has to be earned. One risk, one launch, one breakthrough at a time. Earth's next power revolution, born on the moon. So where do we go from here? Interlune's success could ignite a second space age, one driven not by exploration for glory, but by the urgent needs of Earth. Energy, technology, innovation. The moon could become the ultimate fuel station, powering clean cities, supercomputers, even Mars-bound missions. The moon, once a symbol of distance, could become the beating heart of Earth's progress. But there's also a moral dimension. Will we treat the moon as just another place to exploit? Or will we learn from our past mistakes on Earth and create a model of sustainable, respectful resource usage in space? That's a question for all of us. Final thoughts from KM's Celestial Journey. What Interlune is attempting may sound like science fiction, but it's not. It's real, it's happening, and it's happening now. Mining the moon for helium-3 could reshape the world, not in decades, but possibly within our lifetime. We stand on the edge of something monumental. And here at KM Celestial Journey, we'll be watching every step, bringing you the stories that matter from this cosmic frontier. From Seattle to the Sea of Tranquility, from dusty lunar craters to glowing data labs on Earth, the journey of helium-3 is just beginning. And so is humanity's greatest adventure yet. Stay tuned. Because the moon is no longer just a light in our night sky. It might just be our brightest hope for the future.